Hi, in this lecture, we are going to start our treatment of gas exchange between the alveoli and the blood. When we look at the movement of gas, like oxygen or CO2 from one compartment to another, we typically would think about it in concentration gradients. We would say that if there's a greater concentration of oxygen here than over here, that oxygen would naturally diffuse this direction towards the area that has a lower concentration. And this is how we thought of movement of molecules or passive movement of molecules so far. We've always thought of it in terms of concentrations and concentration gradients, showing us which one has more. Well, we know that whatever that substance is will want to move towards a compartment with a lower concentration. The problem is that we are now dealing with two different mediums. Inside the body, we're always dealing with a fluid to a fluid. But now we're dealing with an airspace to a fluid, the alveoli to the blood. So concentrations don't quite apply. Here's why. The atmosphere here has 21% oxygen. That means if I collect a box of air, 21% of the air molecules in there are O2. If I take a particular cup of water and I expose it to this air, so I'll take my lid off and expose it to the air and let it sit there, well, eventually some of that oxygen might come in, some of the oxygen might come out, some might come in, some might come out. And at some point, the water in my cup is going to reach equilibrium with the air. The air is still going to be 21% oxygen, but my water is not going to be 21% oxygen. And that is because oxygen is poorly soluble in water. Oxygen is nonpolar, it doesn't like water, so it doesn't go into water very easily. CO2 is slightly more polar and so is slightly more soluble in water, but still it's not going to reach the same that we would get out here. But yet at some point they reach equilibrium. So I need to know, has the amount of oxygen here reached equilibrium with the oxygen in my fluid or in my blood, or is there a gradient that's still going to allow them to move one direction or another, from the alveolus to the blood or from the blood back up to the alveolus? And I can't use concentration gradients because the numbers are too different. So I'm going to use a different tool, and that is called partial pressures. So partial pressures are going to be the tool that will allow us to predict, will oxygen or CO2 move from this compartment to that compartment, from that compartment to this compartment, or are they at equilibrium? And so that's the basis of this particular lecture. But before we start our dive into the discussion of partial pressures, I first want to talk about some anatomical designs in the lungs that help make sure that we get as much gas exchange as possible. So our goal is going to be to exchange as much CO2 and O2 between the air and my blood as possible. And there's a couple anatomical designs that really help this. We know that when we're looking at diffusion of anything, distance matters. When I've got two compartments that are separated by a wide berth, it takes a lot longer for the molecules to get all the way to the other side. When I bring those two compartments together, they move much faster. So in the same way, I would want to minimize the distance between my alveolus and my blood, and you can see anatomically that is done here. There's the alveolus, there's the blood. The cells separating those two are simple squamous cells, a single layer of very flat, thin cell. And moreover, they even share a basement membrane to help reduce that distance. So this is a really small distance here. Later on, in a different lecture, we're going to look at some diseases that might impact one of these three things. Are there diseases that increase the distance between the blood plasma and the alveolus airspace? And what is the consequence of that? Not as much oxygen gets into the blood. And so you have a lower oxygen saturation level in your blood. And you can pick that up on an oximeter that you stick your finger into. Another anatomical feature that helps maximize gas exchange between the alveolus and the plasma is to simply make sure that they have multiple opportunities to engage with each other. And this is done by increasing the surface area. By increasing the surface area of the alveolus, I actually have to make sure that my blood runs like this instead of like that. And so in other words, by making it kind of loopy, I have to run my blood around all those loops. That gives my blood more time to interact with the alveolus. In a prior lecture, we were introduced to emphysema, which is a disease where some of the alveolar surface area is degraded. And as a consequence, there's not as much surface area. And then finally, we want to maximize the gradients. We know that if I have a really strong gradient, I'm going to get more gas to move over to the lower concentration gradient than if I have a weak gradient. So that's certainly true for concentration gradients, but it's also true for partial pressure gradients, which is the term we're going to use. So what can help influence the gradient? Well, this isn't so much anatomy. I mean, there is some anatomical component to it, but this is ventilation. By ventilating, you are increasing the amount of fresh oxygen that comes in and therefore increasing the gradient. Okay, now that we've looked at this, let's turn and start looking at partial pressures. So partial pressures are a tool that help us deal with this problem. Gases behave differently in water and air. So even though they have reached equilibrium, they will not be the same concentration. So I cannot use a concentration gradient to tell me which way a gas is going to move. If I tell you that it's 100 millimolars up here of oxygen and 5 millimolars in the water, and I say, is that at equilibrium? Is oxygen going to move into the water, or is oxygen going to move out of the water back to the air? I don't know. You would want to say from 100 to 5, right? 100 to 5. And it's actually pretty close to equilibrium. And again, that's because oxygen is poorly soluble in water. So, as part of calculating partial pressures, we need to understand two things. We need to understand the percentage of gas that makes up a box of air. If I take a box of air and I look inside, which gas molecules are in there? And here are the big ones that we need to be aware of. 21% of the gas molecules you find is going to be oxygen. 0.04% is CO2. Sadly, that number just keeps going up because of greenhouse gases. I used to say it was 0.03, and now I have to say it's 0.04. That might not seem like a lot, but it's plenty when it comes to trapping heat. And then a lot of it is inert nitrogen gas, which unless you're a scuba diver is not something that we're going to worry about. So for scuba diving, it can contribute to something called the bends, which can be fatal, and certainly is in consideration when you think about how you ascend after a dive. But again, this is not scuba class. We're not going to worry about it. So we're really just interested in oxygen and CO2. In terms of an atmospheric percentage, those numbers don't change. If you're here at sea level in San Diego and you get a box of air, 21% is going to be oxygen, 0.04% is going to be CO2. If I go to Denver and I get a box of air, 21% of it's going to be oxygen, 0.04% is going to be CO2. So unless you're like in a room where there's no ventilation and the CO2 levels are building because you're breathing, those numbers don't change. So for our purposes, if I'm saying atmosphere, like what's out here, 21% oxygen, 0.04% CO2. The other thing that we need to be aware of is that the air does in fact thin as we move up in elevation. So when you start climbing mountains and you go up in elevation, the air gets thin, which means that there's less and less air. It's still, take a box of air, 21% oxygen, 0.04% CO2. But if I'm up at Denver compared to San Diego, there's simply just less air in there. The amount of air in a box definitely decreases as you go up. But whenever you take that box and open it up, it's 21% oxygen, regardless of how much is in there. So there's a total atmospheric pressure that does change with elevation, and then there's the percentage, which really doesn't change. So now let's get some practice calculating the partial pressures. Assume that we are at sea level. At sea level, the atmospheric pressure is 760 millimeters of mercury. That is the term that we use, millimeters of mercury, and 760 is kind of our standard sea level. The atmospheric pressure will always be given to you in a problem if I'm asking you to calculate something. The oxygen concentration doesn't change at 21%. So the partial pressure is calculated as the total atmospheric pressure multiplied by what percent of it was oxygen. So in this case, the total atmospheric pressure is 760 millimeters of mercury. It means together, everything is 760 millimeters of mercury. But oxygen is only 21% of that. So if I were to take that box of 760 millimeters of mercury of pressure, and all the little gas molecules are in there pushing against the box, and I take out all the nitrogen, all the CO2, all the everything else, and I'm only left with oxygen, well, that's what that partial pressure means. It means what is the pressure of this box of air because of the oxygen. So we have a way of writing that. It's a capital P and a subscript of the gas, and you can see that here. So calculating it out, it's 760 millimeters of mercury times 0.21. Go ahead and get a calculator and solve it. So hopefully you did, and you get 160 millimeters of mercury. Okay, this is a picture that I'd like you to spend just a little bit of time on, that's showing the partial pressures of oxygen and nitrogen. It doesn't show CO2, but it does show oxygen and nitrogen. And again, it's the total is 760. Nitrogen is the most common gas, so we expect it to have the greatest impact on the pressure. Oxygen is only responsible for about 1/5 of the molecules, so we expect it to have about 1/5 of the pressure. Okay. Let's try some more examples. Pause the video and see if you can calculate these. Let's start with the CO2. Remember that partial pressure is going to be the atmospheric pressure, which I give you, 760 millimeters of mercury, times the concentration of CO2. Well, CO2 represents 0.04% of the total number of gases. So converting that into a decimal is 0.0004. So 3 zeros and a 4. And you get something like this. So your answer should be 0.3 millimeters of mercury. Now let's consider an example where we're back to oxygen. Here I'm telling you that you're at 500 millimeters of mercury atmospheric pressure. This would be the pressure that you might experience on a mountain that's between 12,000 and 13,000 feet in elevation. That's a pretty tall mountain. So how would we calculate this? The partial pressure of oxygen would be equal to 500 millimeters of mercury, because we're at elevation, so there's less air, but it's still 21%, times 0.21, 105 millimeters of mercury. Okay. So this is a very busy image, but I want to take some time to walk you through it to show you that the concentration gradient and the partial pressure gradients are not the same thing. And so we only want to look at partial pressure gradients. So here on the very left, we are looking at some fluid that has zero oxygen in it, none whatsoever. We start with no oxygen, and we expose it to air at a 12,000 foot mountain that has a partial pressure of 100 millimeters of mercury. So at sea level, the partial pressure of oxygen is 160, but here we're just using 100 for simplicity. Now we are going to go ahead and allow that oxygen to move. It bounces around. A lot of it stays in the air. A little bit goes in the water, but not that much. And at some point, the number of oxygen molecules diving in the water equals, there's a dive in, equals the number of oxygen molecules coming out of the water. At that point, we have reached equilibrium. So this is showing equilibrium. Notice that the concentrations are not equal. In the air, we have 5.2 millimolars, but in the water, it's 0.15 millimolars. That's drastically different. They are not in equilibrium from a concentration perspective. However, they are in equilibrium because there is no net movement of that gas one way or another. So we know that the partial pressure in air was 100. And to denote that equilibrium has been reached, we then apply whatever number we calculated in air, and we say, okay, whatever this is equilibrium. It also has the same partial pressure. It's really weird the first couple times you see it, because technically the partial pressure in a fluid doesn't mean anything. All it's saying is it's saying relative to the air, are we lower, are we higher, are we the same? Let us say in this image here, it's the middle fluid, I tell you that the partial pressure of oxygen is 50 millimeters of mercury, and it's 100 up here. That would tell you that oxygen is still diffusing into the fluid. If I tell you that this number down here is 120 and this number is 100, that would tell you oxygen's moving out of the fluid into the air. So gases always move down their partial pressure gradient. They move from a higher number to a lower number. So we're finally left with these rules and considerations. From here on out, we are not going to talk about concentrations because, again, gases between air and liquid do not move down their concentration gradients. They move down their partial pressure gradients. So this is big. Gases move down their partial pressure gradient. Over time, you're simply going to learn to look at the numbers. If I give you a compartment and it says 130 and then another compartment says 100, you know that gas is going to want to move from 130 to 100. That's it. That's what you're looking for. Partial pressure gradients. Partial pressures can be easily calculated in air if you know the atmospheric pressure. And if you're in my class, I would always give you the atmospheric pressure. You will have to memorize that oxygen is 21% and that CO2 is 0.04%. As a rule, when two systems are in equilibrium, whatever the partial pressure was over here is now equal over here. So if we started with a partial pressure of air of 150 and the fluid had a partial pressure of 20, and now over time the fluid and the air have reached equilibrium, the fluid is now given the same partial pressure as the air. And then finally, you will need to be able to calculate the partial pressure of oxygen if I give you the total atmospheric pressure. All right, so that ends our introduction into the weird world of partial pressures. In our next lecture, we will take a look at how the partial pressure gradients of oxygen and CO2 change as we move through the body.